Welcome to lesson 14.3. We are going to talk about behavior of gases. So there are these things called weather balloons that people will use in order to study what the weather is in high altitudes. So what they do is on Earth's surface, they are going to fill a balloon, a specific type of balloon, with really low density gas. And what happens is, because of the laws that we know have to do with gas, when you put gas into a container, the gas particles are going to fill up that container and take up all of the space, which means they're going to be bouncing against each other, and that means they're going to be bouncing against the wall of the container. And so as they bounce on the wall of the container, they are putting pressure against that wall. So when you have this, a weather balloon, you are putting this gas in and then you're going to release it into the sky. As the weather balloon makes its way higher and higher, the pressure of the altitude as the balloon gets higher is actually going to decrease on the outside of the balloon. But on the inside of the balloon, it's going to remain the same, right? And so when you have this difference in pressure, the balloon is actually going to expand, and it's going to expand a lot, about 30 to 200 times the original height. And so when we talk about Boyle's law, we're talking about the relationship that there is between gas, pressure, and volume. And you can actually see that in the way that a weather balloon works. Let's talk about volume and pressure. So when we talked about the weather balloon, we know that balloons are flexible, therefore their volumes can actually change. When you increase the volume in a weather balloon, the volume inside of the weather balloon is actually going to increase as the external pressure changes as it goes higher in altitude. So volume increases in weather balloon until the weather balloon can't contain it anymore, and it's actually going to pop. And what's going to happen is there's a sensor inside of the weather balloon that when the weather balloon pops, it will fall down to the earth, and they can collect it for more information to collect what the temperature is in high altitudes. And so when we talk about gas and pressure, one of the questions is what happens when the volume, when you decrease volume, and what happens to the pressure of gas. So the pressure of gas depends on how many times gas particles are actually going to hit the wall of a container. So if you have a smaller container, you're going to have those gas molecules hit the walls of the container a lot faster because there's less space. Therefore, you're going to have more pressure. And the same thing is with the opposite. If you have a larger container, the gas particles have more space to spread out, so they're going to still hit the walls of the container, but they're not going to hit it as fast and with as much pressure. Therefore, there's going to be a difference in, you're going to have less pressure. So Boyle's law is pretty much talking about the properties of gas. It's going to talk about how if you have a decrease in volume of a container with constant temperature, you're going to have an increase in the gas pressure because of smaller container equals more times and more force the gas particles are going to hit the wall, therefore you're going to have more pressure. So this is pretty much what I talked about. So if you look at the diagram, you can kind of see what happens when you have a larger container, the first one, so you have more room for the gas particles to move around, so they're not going to hit the walls of the container with as much force, and it's going to take them a lot more time to hit the walls of the container, therefore you're not going to have as much pressure. But as you decrease the volume that the gas particles have to move, you are going to have more pressure because now the gas particles are able to hit the walls more frequently and with more force. And this is basically all happening when you have a constant temperature. And that's what Boyle's law refers to. It's how these properties of gas react when you have the same temperature throughout. So Boyle's law has an equation. The equation is going to be the initial pressure times the initial volume equals the final pressure times the final volume. Make sure that you are clear in labeling which is the initial pressure and initial volume, and make sure you're clear in labeling which one is the final pressure and final volume. So you can see that the initial pressure is abbreviated with the little I, same thing with initial volume, and the final pressure and final volume are abbreviated with the little f. So let's talk about, let's do a couple sample problems. Obviously, this one gives you the answer, so let's figure out how we get to 235 liters. So the question asks, a weather balloon has a volume of 100 liters when it is released from sea level, where the pressure is 101 kilopascals. Remember, unit for pascal for pressure is pascals. When we're talking about this problem, we're going to see how we're actually not going to have to convert kilopascals to pascals because they're going to actually cancel out. So I'm going to start over and read the question again. A weather balloon has a volume of 100 liters when it is released from sea level, where the pressure is 101 kilopascals. What will be the balloon's volume when it reaches an altitude where the pressure is 43 kilopascals? So let's figure out how to do this. All right, so for problem 3, let's first, as always, write out the equation. So it's going to be pressure initial times volume initial equals pressure final times volume final. And then let's figure out what they give us in the problem. So in the problem, they tell us the initial volume, which is 100 liters. They tell us the initial pressure, which is 101 kilopascal. They tell us the final pressure, which is 43 kilopascal. And then they tell us we have to find what the final, let's do that again. The final volume is. And so, in order to do that, let's plug it into the equation. So, we know that the initial pressure is 101 kilopascal times the initial volume, which is 100 liters, equals 43 kilopascal times, we don't know the final volume. So what we're going to do is, in order to get the final volume by itself, because that's what we need to find out, we need to move this to the other side. If we're multiplying on this side, to get it to the other side, we need to divide. So we're going to do 101 kilopascal times 100 liters divided by the 43 kilopascal from the other side equals our final volume. Now, one thing you notice is that there's a kilopascal on top and a kilopascal on bottom, which means they can cancel out. Now we can do 101 times 100 divided by 43, and that will be 10,100 divided by 43 equals our final volume, and our final volume will finally equal 235 liters because we're finding the final volume, and that is our answer. All right, problem 20 says a volume of helium occupies 11 liters at a pressure of 98 kilopascal. What is the new volume if the pressure drops at 86.2 kilopascals? Again, the answer is going to be 12.5 liters. Let's figure out how we get there. So for problem 20, before we start, we're going to have to write the equation. Always, always, always write your equation. So P initial times V initial equals pressure final times volume final. We know that the initial volume is 11 liters. We know that the initial pressure is 98 kilopascals. We know that the final pressure is 86.2 kilopascals. And we know that the final volume, we don't know the final volume. That's what we need to find out. So we're going to plug it in. So initial pressure is 98 kilopascals times the initial volume, which is 11 liters, times the final pressure, which is 86.2 kilopascals, times the final volume. So in order to get volume by itself, again, we're multiplying on this side, so to get to the other side, we need to divide. So 98 kilopascal times 11 liters divided by 86.2 kilopascal. What do we do with the kilopascals? We cancel them out. So we do 98 times 11 divided by 86.2, and that will give us 12.5 liters is our final volume. We are going to skip the challenge problem 21, and then we're going to continue with the next slide. Okay, so when we talk about Jacques Charles, he was actually a French scientist, and he was talking about temperature and how that relates to the volume of gas and pressure. So he said that when you increase temperature, you increase the volume of the gas, you will get an increase in the volume of gas as long as the pressure of gas stays the same. So again, he said if you increase the temperature, so the hotter it gets, the more volume of gas you're going to have as long as you have the same temperature. And the opposite is going to be true as well. If you decrease temperature, you're going to get a decrease in volume as long as the pressure stays the same. And that's what you're going to see in the graph shown here. Now, Charles' law can actually be explained with the kinetic theory of matter, which we talked about in the previous sections. So if you heat up gas, the gas particles are actually going to start moving a lot faster than if you decrease the temperature. So now that you have gas that's heated up, you have gas particles that are moving a lot faster. That means they're going to hit the wall of the container that they are in a lot more forcefully and also more often. Therefore, you're going to have more pressure buildup. So let's talk about the equation for Charles' law. This one is you're using volume and you're using temperature, and you're still having initial compared with the final. So the initial volume over the initial temperature equals the final volume divided by the final temperature. So initial volume divided by initial temperature equals the final volume divided by the final temperature. So let's look at problem 4. It says a 2-liter balloon at room temperature, which is 20 degrees Celsius, is placed in a refrigerator at 3 degrees Celsius. What is the volume of the balloon after it cools in the refrigerator? One thing that you need to know is that temperature in the Charles law equation is measured in Kelvin. So if you see Celsius, we need to convert it to Kelvin. If you remember how to convert it, kudos to you, but if you don't, it's okay. I'm going to tell you. So when we have to convert Celsius to Kelvin, we have to add 273 to whatever the Celsius is given. So let's take a look as we solve this problem. Okay, so the first thing we're going to do for example 4 is write out the equation. So initial volume divided by the initial temperature equals the final volume divided by the final temperature. So the initial volume is 2 liters. The initial temperature is 20 degrees Celsius, which is room temperature. Now, remember I said we have to convert this to Kelvin. So you're going to add 273, and that's going to give you 293 Kelvin because the temperatures are going to be measured in Kelvin. So always convert it, and this is, you would just add 273. We don't know the final volume, and we know the final temperature is 3 degrees Celsius. Again, you're going to add 273 to 3 degrees Celsius, and you're going to get 276 Kelvin. All right, so now let's plug it into the equation. So initial volume is 2 liters divided by initial temperature, which is 293 Kelvin. We're looking over here. We don't know the final volume, and we know that the final temperature is 276 Kelvin. Okay? Now we're going to get, we have to get V final by itself. So if we are dividing on this side, in order to get the 276 to the other side, we have to multiply. So remember, you have to, when you move this over, since it's a fraction on this side, or not a fraction, but it's being divided on this side, you have to make sure that you keep whatever I circled in green in parentheses, and make sure you multiply the 276 by the entire thing that's in the parentheses. Okay, so remember order of operations, you do whatever's in the parentheses first. So you're going to do 276 times whatever's in the parentheses. And then you are going to get, give me 1 second, let me put in my calculator. I got the final answer, but I didn't do what's in the parentheses for you guys. So it's going to be 2 divided by 293, which is going to give you a funky decimal, which I'm going to round up to this. Then you're going to multiply that by 276. So if you multiply 276 by 0.007, you are going to get approximately 1.9 or 2. And make sure you use your units of 2 liters. So I know it says 2.3 liters here because this answer was taken from the textbook, but the textbook actually has error where they copied the wrong temperature again. So the answer is 2 liters, which we just did together. Ignore the 2.3 liters. Okay, so problem 22. You are going to do the same thing again as we just did in the previous problem, but instead of doing using negative 18, instead of using 3 degrees Celsius for the final temperature, you're going to use negative 18 degrees Celsius, which only means that you are using negative 18 plus 273 instead of 3 plus 273, and then you're going to get your answer. So let's do this together. Okay, so again, first thing you're going to do is write the equation, which I'm going to do here. Then we're going to plug in. So we know that from the previous problem, problem 4, we're going to use the information that initial volume is 2 liters, initial temperature is still 20 degrees Celsius, but remember, we're adding 273 to get Kelvin, which is 293 Kelvin. We don't know what the final volume is still, because now we're given a new temperature, which is negative 18 degrees Celsius, but to get Kelvin, we're going to add 273, and that's going to give us 255 Kelvin. All right, so now let's plug it in. So we're going to do initial volume is 2 liters divided by initial temperature, which is 293 Kelvin, equals, we don't know the final volume, and we know that the new temperature we're using is 255 Kelvin. So we're going to, again, if we're dividing on this side, we're going to do the opposite, which is multiply. So 255 Kelvin times 2 liters over 293 Kelvin equals a final volume. Now, one thing I forgot to mention is you have Kelvin here and you have Kelvin here, so they can cancel out. So always do what's inside the parentheses first, order of operations, then multiply by what's on the outside, and you will get about 174 or 1.8 liters. You can kind of round it up. This might vary for some people, but you can either leave it as 1.74 or round it up. You can round it up, or you can leave it as it is.